Welcome back to the course of chemical crystallography. In the previous lecture, we have discussed about the unitary structure factor and normalized structure factor expressions, and we are now ready to explore the different methods that are used in direct method for structure solution. So today we will start with a portion where we would like to see the method where we use the method of sigma 1 relationship. This sigma 1 relationship is applied in most of the cases of centrosymmetric structures. So we use sigma 1 relationship in centrosymmetric structures. In case of these centrosymmetric structures, the phases of various reflections can be 0 or pi. So the phases for centrosymmetric structure is restricted between 0 and pi. So the idea is to estimate the phase of a reflection 2h, which means 2h plus 2h 2k 12 based on the phase of reflection h, which means HKL. So when we write the plane H, it means we are talking about the plane HKL. When we write the plane 2H, we mean that the plane is 2H 2K 12. For example, if it is 1 1 0, then it will be 2 2 0 and so on. So if we write EH, it is for the plane HKL. You can write E2H is for E2H 2K 12. So now, as we know that in case of centrosymmetric structures, the phases can be just pi and 0. Now let us use the 1 1 0 and 2 2 0 reflections to understand the sigma 1 relationship. Let us try to first draw the projection of an oblique lattice like this, and then we are trying to draw first the 1 1 0 set of planes, which are like that, are the corresponding 1 1 0 set of planes. We mark these lines as 1 because they are identical planes. Now, in case of these 110 reflections, the maxima of the electron density will appear close to 1 and the minima will appear close to the lines which I am drawing in between and marking them as 2. So, the electron density maxima for 110 planes with, we assume, the phase phi equal to 0 will be close to lines 1 and the minima will be close to 2. So, where would the 0 of electron density lie? The 0 of electron density would lie in between 1 and 2, which I am drawing here as dashed lines. So, that dashed line will indicate the 0 electron density for this 110 set of planes. So, the minima, the 0 of electron density will be close to the lines marked as 3. So, what will happen is the possibility, if the mod EH is large and phi is equal to 0, what we will see is the large electron density close to the lines marked as 1 and minima will be close to 2 and 0 will be close to 3. So, now if we try to see what happens for the planes 2 to 0, the reflection 2 to 0, if again for 2 to 0 E2H is large at phi equal to 0. So, what are 2 to 0 lines? The 2 to 0 lines are now the lines which are marked as green, the number 2. And eventually, this middle line also becomes the 220 as well, and so on. So, now for 220 set of reflections, the electron density maxima would be close to both lines 1 and lines 2, because you can see both lines 1 and lines 2 correspond to the same 220 set of planes. So, the maxima will be close to lines 1 and lines 2, and minima would be close to 3. So, if both EH and E2H are large and phi H is 0, then phi 2H also has to be 0. Which means that the electron density for this particular crystal, where both EH and E2H are large, we should see a large electron density associated with the lines which are marked here as 1, where these are coincident, where the electron density maxima is for both 110 and 220, will have a lesser density near the 2, because in case of the line, in case of 110 reflection, the lines along 2 will have minima, whereas in case of 220 will have maxima. So, these lines will have intermediate density, and the lines 3 will have 0 intensity, because line 3 is now minima for 2 and 0 for 1, that is, it is 0 for 100 set of reflections and it is a minima for the 200 set of reflections. So, there won't be any density close to that. So, one can conclude that if E110 is large and phi 110 is 0, then the atoms will be close to 1, the electron density maxima, and 2 would be minima with 3 as 0 density. Similarly, if E220 is also large and phi, that is the phase of 220, is also 0, then the atoms will be close to both 1 and 2, and 3 would be a minima. Which indicates that the plot we had drawn in the previous slide, which I am trying to bring it here as well, indicates that so this plot here then describes what I have written here. So the probability of finding atoms will be maximum in the regions near the line 1 if both the conditions are satisfied. If a different situation arises, so if if E2H is large when phi 2H is phi 2H is pi, then the electron density is maximum near the lines marked as 3 and minima near the lines 1 and 2. So this represents a situation where there is no overlap regions. If you can see in this figure, if we have additional electron density, if it is E2H is maxima at phi equal to pi, then the regions marked as 3 will have high density and regions marked as 1 and 2 will have low density. So overall the 110 and 220 sets of reflections will not have any overlap of intensity, and hence a different scenario will be represented. So by looking at the high values of EHKL and then incorporating two different values of the phi, that is phi 2H, we get two different scenarios, and from that we can conclude whether it is the phi for 220 is 0 or pi based on the electron densities that we can see by doing the corresponding Fourier transformation. So what is then done is, first you assume that the phi for 110 reflection is 0 and do a Fourier transformation, get the electron density plot. then you do it for the HKL, which is 220, assume it to be 0 and do the Fourier transformation and see the electron densities, and then you do it again for phi equal to pi for 220 reflection and see that there is a difference, and based on these one then can solve the values for the electron density for the coordinates for the atoms close to these particular two reflections. So this method is then applied to all possible reflections which are related by just integral multiple of HKL. So for large values of EH and E2H, would indicate that both IH and I2H should have the same phase, phi equal to 0, or both should have phi equal to pi. So this conclusion that we are drawing here is called the sigma 1 relationship. So I would like you to practice or to do this exercise for phi equal to pi for both E110 and E220 set of reflections or E220 structure factors, and draw the scenarios that I have drawn and make sure that the sigma 1 relation is still valid. You can also try when phi equal to 0 for HKL, maybe for 110, and phi equal to pi for 220 reflection, and see what kind of electron density distributions that you get. So this is one of the methods for getting the phases of one particular reflection compared to the phase of another reflection having same or large intensity. So now I would like to also introduce you to another relationship which is called the triplet relationship. This triplet relationship is based on the values of large values of EH, EK and E minus H minus K. Remember, EH corresponds to IHKL, EK corresponds to I H prime K prime L prime, and E minus H minus K corresponds to I minus H minus K, corresponds to I minus H minus H prime minus K prime minus L prime. So, what we are trying to visualize is the following. If we have set of HKL planes drawn like that as EH, or the planes I mark them as simply H, and then we mark another set of planes like that and write them as Ks, and what we are trying to say is that we have large value of both mod of EH and mod of EK. So, both the planes HKL and H prime K prime L prime have large electron densities. So, that means when these two sets of planes interact the way the intersect the way I have drawn here, the points of intersection are the points where the electron density should be the maximum. Or the electron density should be very high, because we are saying that both the EH and EK have very high magnitude of structure factor amplitude, that is, the scattering is very high in those two planes. So, the plane which actually bisects these two planes, I am drawing it in a different color for easy understanding. The planes which are now marked in purple are passing through the points of intersections of these planes. The Miller indices of these planes are nothing but minus H minus K. So, from this observation of the values of EH and EK, one can also conclude that the value of E minus H minus K, that is the diffraction from those set of purple colored planes, will also be high or large. So, this also represents a situation where by observing two different reflections of different HKLs, one can then say that a third reflection will also have a very high value of EH, and if the phases of EH and EK are same, the phase of E minus H minus K will also be the same. So, in a centrosymmetric structure, if we see that the phi H is 0 and phi K is also 0, then one can conclude that phi of minus H minus K will also be 0 and all three will be of very high intensity. So, this is what is called a triplet relationship in X-ray crystallography, which also helps us in structure solution by direct methods. So, today we have learnt about two relationships, one is sigma 1 relationship and another one is triplet relationship in direct methods. So, we will continue in this direction and try to understand the basics of direct methods in the next few lectures.